Welcome back. Today we're going to be talking about constant acceleration, or the other term that we use is uniform, and you'll recall we've already talked about uniform or constant velocity. When talking about acceleration, acceleration is defined as the rate of change in velocity with respect to time, and it is a vector quantity. So again, that means that direction matters. So what that means then is if an object's velocity is changing in any way, it's accelerating. And there are three ways that this can occur. The velocity can change by the object speeding up. The object's velocity can change by it slowing down. Or its velocity can change by changing direction. Again, because velocity is a vector quantity, so direction matters. So velocity is a vector, and acceleration is also a vector. Okay? And the vector nature of both of these is very important. Now, for our average acceleration, the average acceleration is the total change in velocity over the total time taken for that change to occur. And hopefully this looks a little bit familiar. When we talked about average velocity, perhaps you'll recall that the average velocity was the total change in position over the total change in time, or xf minus xi over tf minus ti. So similarly, our average acceleration is the total change in velocity over the total time. We'll be looking at primarily cases where the acceleration is uniform, hence the constant or uniform acceleration title. But there will be times when the acceleration may change. Just recognize that the average acceleration and the instantaneous acceleration are only the same when the acceleration is uniform. So let's jump right into an example here. We have a car speeding up from 7 meters per second to 25 meters per second in 4.5 seconds. So as with any type of problem that we're working through, we want to list our variables. So our VI in this case is 7 meters per second. Our VF is 25.0 meters per second. And our time is 4.5 seconds. So as we said, average acceleration is equal to delta V over delta T, which is equal to VF minus VI, and we can just say delta T because we're given the total change in time. So then we have 25 meters per second minus 7 meters per second over 4.5 seconds, and so I've waited until the very end to plug in my numbers. So then I have 25 minus 7 is going to be 18 per second over 4 seconds. So that gives us 16, 4.5, and looking at our units, meters over seconds, our units are as such. Now let's focus on our units for just a moment. If we rewrite this, meters over seconds over 1, an equivalent to that is meters per second times 1 over s, right? We can divide, if we divide a fraction by another fraction, it's the same thing as multiplying by the reciprocal. So that gives us units of meters per second squared. And this is how we'll typically write our units for acceleration, meters per second squared. But I think it's important to understand that it's really meters per second, which tells us the change in velocity, or the change in the meters per second every second. Now, similar to, again, how we did this with our finding our final position, we can also derive an equation for the final velocity. starting with our definition of acceleration, which is the change in velocity per unit time, we expand that and say that the acceleration is Vf minus Vi over t. We want to solve for the final velocity, so we want to isolate that variable. So we're going to multiply both sides by t, which gives us At equals Vf minus Vi. I'm going to add Vi to both sides, so it cancels out here. And what we're left with is final velocity is equal to initial velocity plus A times t. This A delta t, or A times t, represents the change in velocity. Our initial velocity is of course whatever it is, so what we start out with plus the change in that value gives us our final velocity. Now graphically, again, hopefully we see a lot of the similarities between uniform velocity and uniform acceleration. Previously we looked at a change in position over change in time graph, and we saw it to be linear. That gave us a constant change in velocity, or a constant change in position, which is a constant velocity. Here our graph is delta V, so we're graphing delta V versus delta t, and what we see again, it's a linear relationship where y equals mx plus b. So here's our linear equation, and in this case our y value is v. And actually we can probably take that off if we want to. We don't have to. But our slope is the acceleration, and our x value is the time. And so similar again to how we were able to determine the velocity from a position time graph, we can also determine the acceleration from a velocity time graph. And in instances of uniform acceleration, because it's uniform, the final and the initial are always going to be the same, which is what ultimately gives us the uniform slope. Now a little bit more on the vector quality of acceleration. So overall we have a couple of things going on. If the object is speeding up, the acceleration is in the same direction as the velocity. If an object is slowing down, the acceleration is in the opposite direction of the velocity. Here's where we have to be really careful about our signs and understand that with vectors in one dimension, positive and negative is simply a way to distinguish between direction. So if I call to the right positive, let's do this, positive, negative. If I have an object that has a positive velocity, so it's moving to the right, and the acceleration, the change in velocity, is also to the right, then in this situation, the speed will increase. So we have a positive velocity, positive acceleration, the speed increases. If on the other hand I have a positive velocity and a negative acceleration, so the acceleration is in the opposite direction, this is going to cause the speed to decrease. So that's with a positive velocity, or a velocity in the positive direction. But what if the velocity is in the opposite direction? So here I have a negative velocity based on our current frame of reference. If I have a positive acceleration, and this is where it's important to understand that positive is simply a direction. Because we have a positive acceleration, but because the two things are in opposite directions, because the velocity and the acceleration are in opposite directions, our speed is actually going to decrease here. So even though you have a positive acceleration, the speed of the object is getting slower. Now the other piece of that then would be, if I have a negative velocity and a negative acceleration, even though I have a negative acceleration, because the acceleration is in the same direction as the velocity, the speed of the object is going to increase. Okay. Now, if they're in two dimensions, if we have two-dimensional motion going on, then an acceleration that is, let's say if our velocity is like this, let's say the acceleration is in this direction, well then you're going to have the direction of the velocity change. So it might be traveling in this direction afterwards. That takes a little bit more analysis, and it depends exactly on how much the acceleration is, at what angle it is, and so on. So the speed could change, but primarily the direction will change. And as we talk about two-dimensional motion, we'll get into that a little bit more. So we have four primary equations that we're going to be using for uniform acceleration. Our first is what we've previously given as the actual definition of acceleration, change in velocity with respect to time. So that's this one. The second is our equation for final velocity, which is the one that we derived from the definition of acceleration. And then the last two are also ones that can be derived from our original equations. I'll put an example of this, or I'll show how these are actually derived. I'll show the work for this in Schoology, so you can go ahead and take a look at that if you're interested. But ultimately, these two are derived from our other equations, and they simply give us another way to look at our variables, another way to tie our variables in together. This one, this number 3, notice we don't need the time. So we can determine final velocity or acceleration just based on the initial velocity and the distance over which the acceleration occurs. And then this last one, we can solve for the change in position, the total change in position, without knowing what the final velocity is. And we'll talk about these a little bit more in class, but notice that this is a quadratic. And like I said, we'll talk about this when we look at our position time graphs as they relate to acceleration. Now, there's one other piece I want to talk about really quick, definition. And that's a specific case of uniform acceleration, that is free fall. And as we start talking about forces in motion and acceleration, and the idea that acceleration is caused by some non-zero net force, we should recognize that we are all being pulled down towards the earth every moment of our lives, as long as we're existing on the surface of the earth, due to this magnificent force called gravity. And when we drop something and there's nothing under it, it falls. And in that free fall, the objects accelerate at a rate of roughly 9.8 meters per second squared. Now, depending on the altitude, depending on your height above the actual center of the earth, this varies a little bit. We find things fall at slightly different rates at the ocean versus, say, somewhere in Boulder, Colorado. It's measurable, but it's not significant. For our purposes and our calculations, we're going to use the acceleration due to gravity as 9.81 meters per second squared. And so anytime we're given examples or samples or things like that, unless otherwise specified, you can go ahead and use that value, and that'll be sufficient. What this means is that if you drop something like a golf ball, after 1 second, it will have a velocity of 9.81 meters per second. After 2 seconds, it will have a velocity of 19.62 seconds, and so on and so forth, increasing at a rate of 9.81 meters per second every second until it hits the surface of the earth or hits something. Now, in this case, we're not going to concern ourselves with air resistance. or terminal velocity, but these are things that we will talk about more as we get into forces and how forces affect acceleration. All right, make sure you've written down any questions you might have, and we will touch on those at the beginning of class. See you soon.